The system below rotates with an angular velocity omega. If the masses of the rod supports are negligible, so the masses of these beams here, what is the ratio of the angular momentum of the two upper spheres to the angular momentum of the two lower spheres? All right, so angular momentum is I omega. So omega is the same for both of the setups. I is different. So we're going to manually calculate the moment of inertia for this arrangement of spheres versus this one. So we want the ratio of the upper spheres, so that's what we're going to calculate on the top of the fraction. So to calculate the moment of inertia of this shape, that's going to be mr squared plus mr squared for each mass. And this is the distance to the axis of rotation. So the mass is m, the distance is L for each mass. So we have ml squared. Therefore, the moment of inertia for the two top spheres is 2ml squared. Next, let's find the moment of inertia of this shape. So it's mr squared plus mr squared again. But let's go fill in the actual details. So m is 3m. The distance is L over 2. That gets squared. And then we're going to have two of those. So we can just throw a 2 out front because we're going to add the second term. So we're going to multiply this moment of inertia by 2. So what do we have? We get 6m. And then we have L squared over 4 because that 2 gets squared as well. So we can simplify that to be 3ml squared over 2. Now we want the ratio of the top spheres to the bottom. So we're going to take this and put it as our denominator to create that ratio. So we have 3ml squared over 2. Now we're dividing by a fraction, which is the same thing as multiplying by the inverse. So therefore we have, I need some more room here, 2ml squared times 2 over 3ml squared. Now the ml squared is going away, and we end up with 4 over 3. The answer is B.